Hello, this video describes our InnovateFPGA project entry, FPGA-based irrigation system for softfruit farms. Initially aimed for softfruit farms in Scotland, the design concept can also be applied to other regions of the world and to other types of farms. The project used a Thoracic DE10 Nano FPGA system on chip cloud connectivity kit, based on the Intel Cyclone 5 FPGA. The kit is mainly comprised of two parts, a hard processor system portion and an FPGA portion. Signals from the sensors go to the FPGA fabric via an Analog Devices Incorporated ADI shield. Embedded Linux running on the HPS will then be used to send the measured recordings to Microsoft Azure Cloud Services. Initially, the sensors are a capacitive soil sensor, a soil pH sensor, and an RTT temperature gauge. There are also other sensors on an attached Thoracic RFS daughter board. The ADI shield is an Arduino shield form factor board which the three aforementioned sensors are attached. The project aims to reduce water waste of irrigating farm crops. Instead of timed or manual starting of the operation of a water pump, the Intel FPGA-based system will irrigate only when required by measuring the level of moisture in the soil. When an appropriate threshold is reached, the signal from the soil sensor is sent via an analog to digital converter to the FPGA. The FPGA then sends out an output signal to a relay to switch on a water pump if the soil is dry, and then the switch is off the water pump when the crops have the appropriate amount of water. This watering cycle is repeated for the duration of the growth of the crops. The FPGA is registered and added to Microsoft Azure as an Internet of Things IoT application, where it can be managed and readings from the sensors can be monitored. Using a reference design, embedded Linux is installed onto an SD card and used to boot the FPGA, where Linux is then running. The FPGA and Linux have to interface, and drivers are configured from the Thoracic GitHub repository, which contains code examples for use with the Thoracic DE10 Nano development kit. The pins on the Arduino shield have to be configured, and this is done by using the Quartus Prime software application. The design has to be compiled, and the appropriate programming file generated. We also need to update and create a device tree overlay. It describes new elements of added hardware and any new bindings required. With the overlay and the device tree compiled, the files are uploaded to the DE10 Nano board. When the new overlay is running, it will communicate with the sensors. The cloud application can then be developed. The DE10 Nano can be set up with the reference application, which is cloned from the Thoracic GitHub repository. Azure IoT services then have to be configured. A new Microsoft Azure account was created in order for DE10 Nano to be provisioned through the web application. When the application is running and the DE10 provisioned, sensor readings can be displayed on the Azure console. To summarize the setting up and the development kit, a new overlay for the Thoracic Intel FPGA-based cloud connectivity kit is created and connected to Microsoft Azure cloud services, where remote soil sensors can be monitored. The performance of the design will be discussed next, where the following sustainability results and resources may be realized over time. The implementation of our irrigation system saves farmers valuable resources, including water, time, and manual labour. As the crops are watered close to optimum level, it is likely that there would be less time needed sorting out the spoiled crops after the harvest. Over a period of many years, this project has the potential to save a huge capacity of the farm's water. Saving water resources boosts the farm overall sustainability. Over time, and with more sensors added, the farm can be fully optimized in its water usage. Multiple sensors can help scientists and farmers to understand the hydrological and soil dynamics of their cropland, which can lead to a smarter usage decisions at the watershed scale. Overwatering is a constant strain on the soil system. Optimal water usage prevents soil erosion on the farm, therefore ensures livelihood and sustainability farming practices over time because the soil health will be kept in good condition in the future. Soil erosion is a serious long-term threat to farmers. Because soil erosion is a serious issue impacting farming sustainability, due to change in soil composition and the transportation of important nutrients out of the field, this can lead to a decline in crop quality over time. Overconsumption of water releases the soil's organic carbon, which contributes to climate change. The use of our system will help prevent and decrease this, and means the farmer can be more sustainable and last longer. Overwatering and the decline in soil health leads to the release of greenhouse gases, or GHGs, from the soil and decreases the net primary productivity of the soft fruit plants. This decrease in net primary productivity negatively impacts fruit yield. Our system would help prevent this by offering a more sustainable route to the maintenance of soil quality and the carbon storage potential, which helps climate change mitigation. Good quality soil can decrease flooding potential, allowing the farm to sustainably continue production and not waste crops due to flood events. Less flooding means less pollutants and contaminants in the field. Prevention of flooding by healthy soil and the understanding of hydrological parameters through our system saves money, reduces environmental and economic costs due to the promotion of good water and soil health. Our system encourages optimal biogeochemical cycling within the farm's soil and ensures sustainability of the farm. We believe our design proposal can enable local service providers to offer deliverable FPGA-based irrigation system projects to farmers. Thank you for listening.